Hello world! Ever notice how the world around you is, well, solid? Now, there's a complex reason for this, but it pretty much comes down to us not living in some sort of Elon Musk style simulation and physics. The thing is, in a simulation, like this fun game of Fallout 4 that I was enjoying the other day, stuff is also solid, but it's not real. How's that work? Also, how does the other real worldy stuff work in games? Like gravity? Well, let's find out, shall we? Because welcome to Gamedev the Hard Way, series where I attempt to write a computer game for the Agon Light, which is a retro-inspired single-board computer, just using C from scratch. This time, we're looking at collision detection and physics. But don't worry, because if, like me, you're a bit mathematically challenged, there's not lots of impossible maths to wade through. I'm a programmer, which means there'll be lots of impossible C code to wade through instead, which is much more interesting. So, come on, let's have a look. Before jumping into the good stuff, let's take a minute to see what we're actually talking about. Because games are 100% code. If we don't code it, it doesn't exist. It just doesn't magically happen. Physics and solidness, as we'll call it, are a natural part of our world, but a computer has no idea we're trying to represent a world. It could be working at our taxes for all it knows. It's just following instructions. So we need to write some that tell it objects are solid. And what to do if two solid objects touch each other. No, not like that. It's not that kind of video. Collision detection is subtle and it's quite easily overlooked because we take it for granted in the real world, you know? I'm playing a bit of Llamatron here, which, in the comments of my last video, some of you have also got fond memories of. Or possibly they're the only memories that you've got after it's lasered away everything else in your brain. The llama shoots bullets, the bullets hit the enemies go away. If enemies touch the llama, not like that, the llama goes away. Knowing when a sprite is touching another is the collision detection part. It goes along with another thing known as collision resolution, which is doing something about the collision. So one thing knowing the collision has happened, it's another thing deciding what to do about that collision. Here's Rick Dangerous. Our intrepid hero is stood on the floor because the game is constantly trying to pull him through it, but then resetting him back on top of the floor. It's the same mechanic that makes jumping work, but here he is collecting items just by running over them and they vanish. The floor is a solid thing, so we can't fall through it. The items are not solid things though, so we can collect them, because that's how it works in games. You sort of walk over stuff and it's like you've picked it up. We'll look at all of this and how it actually works in this video. The most simple, most basic way to do collision detection is with a technique known as axis-aligned bounding boxes, or AABBs for short. An axis-aligned bounding box is a fancy term for a box that covers the whole sprite. That's the bounding box part. You might also know it as a hitbox. Anything in this box is considered inside the sprite. Being axis aligned just means it isn't rotated in any way. It's literally aligned with the X and Y axes on the screen. It sounds more complicated than it is really. Here's the code. And the first thing we do is an axis aligned bounding box. So here it is. We work out the corners of the box and we see if the box is overlapping. And if the box is overlapping, we're returning 1, otherwise we're returning 0. This code looks really strange, but if you do it with some pen and paper and you put numbers in it, you'll find that it actually works and it's quite interesting. It looks a bit weird just because you can condense it to like one line of code. But if you grab some graph paper, draw 2 overlapping boxes and measure them out, and then put numbers into that code that I've just drawn, you'll see it actually works. The best part is it's really short code, which means it runs really quickly, which is important on our little tiny Agon computer. So continuing my way of abusing this nice sprite editor in ways it was probably never designed for, I'm going to show you how I make collision boxes for stuff. Because it might be that if you've got a sprite, you don't want like the actual 16 by 16 box that it lives in to be the collision box. You might want something smaller. If I zoom this in, rather than just typing in numbers into a config file or typing in numbers into code, I want to visually draw it, because if this is some little guy, I might just want his head to be the collision box. This box, this blue thing in here, is called a slice inside this editor. So to get to it, it's in the slice tool, which is part of the move tool. And what it lets you do is draw a box on the screen. they're not really used for anything in this editor, and there's nothing that loads their data files. It's just a thing they've put in, hoping that you'll find it useful. And I do, because the JSON data that it creates lists these. And I'll show you that in a minute. Another thing that's really useful is I want to say what things can collide with other things. Like, I want the player to be able to collide with enemy bullets, but not its own bullets, because if I shot the player's bullets out of itself and it collides with them, I'll be able to kill myself. And I don't really want that. That's not how computer games work. So I need a way of saying what things can collide with other stuff. Now, I did what I've been doing for everything else. I've been stealing people's ideas. And I've nicked the Godot and I think it's Unity's way of having collision layers and collision masks. The idea that I can say, you are of type player, and you will collide with things of type enemy, and of type enemy bullets, and then enemy bullets will collide with things of type player. There's no way of doing that in this editor, and I don't want to write that in code because I'll either forget or I'll get confused and do it wrong, or it'll just be really tedious when I've got lots of sprites. All the sprite data lives in the sprite editor. I figured out if you look on the layers and go to properties, there's a user data field. So I made up some JSON code and put it inside. So I'm saying this is layer 1 and it's going to collide with layer 12. These are numbers that convert easily into binary. So I've not picked these at random. So here we are in the JSON data that gets created. If I scroll way down to the bottom to the interesting stuff in here. So we've got the frames from before. We've now got a new bit. We've got a layers thing, which has got this JSON data inside it. It's been escaped, but I'm writing the code that unpacks all this, so I can deal with that. So I can pick out what layer this sprite is and what it's going to collide with. I can also pick out the slice, because look, it's got a frame and it's got the bounds in pixels. So that's how I know where things collide. So if we go look in the code that makes use of this, so once I've run it through my converter that turns it into my internal own sprite file, this is what loads that in. And it just reads in all the lump of data, and it assigns it inside a C struct. So it's got a width and a height and a count and a state count. Then it's got the collision layer and the collision mask. So that's the collision layer, and that's the collision mask, those two numbers. It's then got the rectangles X, Y, width, height. That's this blue box that I've drawn here. I can then make use of this in my code. Here is my sprite system update that we saw before, or you're about to see, depends where this appears in the video, because I'm recording this out of sequence. I go through all the sprites, and the first thing I check is the collision layer part of the collision mask for both sprites? So should player bullet collide with player, and should player collide with player bullet? If they don't, we don't do any of this physics AABB stuff. We just go on to the next sprite. So this means I can prune out collisions that aren't supposed to happen just by checking some flags before doing any collision detection at all. Then I can do quite a wide collision detection of just, do their two rectangles overlap? And if they don't, I don't bother doing the physics stuff. If the physics stuff works, I then will also do these collision functions. So collision detection is easy. You just check if things are overlapping. If they do, job done. And like I showed at the start, resolving collisions usually involves making one or both of the sprites just like go away with some sort of flare. You know, you shoot the thing explodes, it looks pretty. That's old games though. It's a bit boring really, if you're honest, you know. It's fun moving the things around the screen and shooting away aliens or Rick Dangerous picking up stuff. But it doesn't really feel that realistic compared to modern games. Also, it doesn't help if we want the game to have solid objects. So we need a way to resolve collisions to make it appear as if things are solid. Doing this gets insanely complex insanely quickly. Collision resolution is where we try to make the objects solid, and our games understand that it's supposed to be a solid piece of ground or a box. The basic idea is that when two items collide, they're probably overlapping each other. In fact, the collision detection code relies on that being a fact. So one way to make them see if they're solid is to see how much an object is overlapping another, then calculate the shortest distance to move them apart so they're no longer overlapping. If you do that in the same frame, you don't see it happening. Another way is to use more complex maths. So obviously guess which one I chose. I was faced with the easy way that everybody does, or the more complicated way. Yes, I chose the more complicated way, because of course I would. I can't ever just pick a thing and make it work, you know? Could have had this written in 10 minutes, like some of you pointed out in the comments. But we're doing it the hard way, because it's fun. Like I've said previously, one of the main points of having anything in a game is that it feels solid, so you can interact with it. This is how I do it. I've got an update function for my player sprite. The first thing I do is I create a vector to hold the direction that the thing should be moving in, and I set it to 0. Then, depending on which key I'm pressing, I set the movement vector to be like appropriately up, down, left, right, or diagonals. I'm also using that to work out which way I should set the sprite to be facing. I then scale the movement amount by what I'm calling the speed, so it's going to move in 10 in whatever direction. I then apply that as a force to the player. To the player. So I pass in, like, if I press up, where's up? There's up. Then I'm setting Y to -1, and I'm setting X to 0. I then multiply that by 10, so I'm going to set the force to -10. There's some stuff for shooting bullets that come out the same place as where the player is and where the player's looking. Feel free to read that in your own time. We'll talk about that another day. So if I go into physics.c, so the position and the velocity, here we go. The acceleration is the force that we just applied, multiplied by the mass of the item. The inverse mass thing means that if I want something that's not going to move at all, I set its mass to 0, and then it can't move because the acceleration will always be 0. It's better than trying to set the mass to be some massive number. And then what if you set the mass to 0 because you want something that doesn't weigh anything? So this is a different way of doing it. Now the collision stuff that happens, so it's a function called physics resolve collision, and it takes 2 physics bodies. But we need to work out where it gets those from. Let's see if Kate can tell me where that comes from. Here it is. See, I really like this editor. Actually, now that I've switched on the LSP server, it now works perfectly. Colours in the text, it lets me jump between code. It's really cool. I like this. So, we have a sprite system update that we had before. We integrate the physics. We then have to test the collisions. And there's a lot of sort of weeding of things out here because I'm doing like nested for loops, which are awful. I should have hopefully explained previously kind of why you shouldn't do a nested for loop. But I'm going through all the sprites, and if the current sprite I'm looking at is active and it has a physics body, I'm then checking that against all the rest of the sprites. And the first thing we do is an axis line bounding box. So here it is. We work out the corners of the box and we see if the box is overlapping, and if the box is overlapping we're returning 1, otherwise we're returning 0. We then have to resolve the collision between the 2 items that we're currently looking at. Ignore this commented out code, I've optimized that away. So the first thing is, if there is no physics object for either of them, we're not doing it. We then work out the difference between the middles of both sprites, and then we work out how much they are between them, which then lets us work out how much they overlap on the X and Y axis, because we need to work out which way to push these 2 things apart. If they're both moving towards each other, when they collide, they need to move away from each other in the same direction. A lot of this physics I'm learning whilst I'm doing it, so talking about it is a little bit confusing. We're then working out how much it's gone in the other one, so that we can work out how much to push it back out so that things feel solid. This is quite important. It's not enough just to know that something is overlapping. We then need to move the things apart just enough that it looks like they never overlapped in the first place. This resolve collision impulse thing works out the speed and velocity that things were colliding at and makes sure that they go away from each other at a comparable speed, including some bounciness, so that if they're really solid non-bouncy objects, they won't bounce much. If they're really bouncy objects, they'll spring apart. I'm going for that sort of arcade game physics where it feels more than just the sprites are moving around the screen. They have a bit of life to them. That's all I want, something that feels slightly more realistic. Once we've resolved the collision impulse, so things are now moving away from each other, we actually need to physically move the items, which is this positional correction stuff. Here, all we're doing is physically moving the items apart from each other so that they're not next to each other and slightly interacting. there's a little bit of fudging where you've got to move things apart, but then move them a little bit further so they're not actually in contact. Otherwise they'll stick to each other. Now we need to fix another point that might not be immediately obvious, but for those of you that are paying attention at the back and have done this thing before, there's a small detail floating about that you might have noticed. You see, the CPU inside an Agon Light is an EZ80. It's the core of a Zilog Z80 from the 1980s, with some extra bits added on to turn it into a modern microcontroller. One of the things they didn't add in was the ability to work with floating point numbers. Now, numbers and how they're represented in a computer will be a future side video, because it's quite fascinating how it actually works, and it goes beyond merely storing data as binary and it goes 1, 2, 4, 8, 16. The short version is, the CPU can't cope with fractions natively. We've got to write some code to deal with that. Now if you think for more than a second, how would you represent 3.6 in binary anyway? Because it only does whole numbers made of 1s, 2s, 4s and other powers of 2. Well, we can write some quite clever code, but it's super slow. So we're going to sidestep that problem using something else called fixed point maths. So I'm going to show you and go on about my fixed point code and how it works, because it's not very big, but it's quite interesting how this actually functions. So like I've just explained, I need to use fixed point maths, and here's some of the code that I've got. So because the Agon CPU uses 24-bit integers, I can use that as my fixed point type. So I can have a 24-bit number, and I'm going to use the last 4 bits as the fractional bits. So I've got some basic things in here, like I always use the number 1 and 2 quite a lot in the maths, and it kept screwing up my maths if I forgot to convert that into the fixed point form. So I've just got that. There are some little things here for absolute minimum and maximum. This bit is doing multiplication, and then this is doing division, because it's not as straightforward as dividing. You've got to watch that you don't divide the number down too small that you can't represent it, or so small that it wraps back around to being a massive positive number. And I've got a square root thing, which I'm not using at the moment, but this is just compiler macros in a header. I have a few other bits of code as well. So here's converting a floating point number to a fixed point number, and this just mostly shifts it, but then also rounds it a bit, and then works out whether we've gone past the end of the number that we can represent, and then cuts it short. This isn't sometimes that important in the fixed point maths if you're doing things, but if I'm doing physics and moving stuff around the screen using vectors and just maths, if my maths goes too big or too small and starts wrapping around the end of the integer, I'm just going to have stuff that explodes off the screen. Now I won't have a clue why it's happening. I might spend like months trying to figure out why stuff just explodes, when really it's just that the numbers get too big or small. Here's how you convert an integer, so you just shift it. With this one, you have to convert it and then shift it, and it's a bit strange. Just doing a float is really easy. So this might look like a lot of code to do fixed point maths, which traditionally you just shift things left and right by a number of bits and call it done. But that can have some problems. Like my compiler kept warning me that if I was just trying to multiply a fixed point number by shifting it, because it's a signed integer, it was whinging that doing shifts on a signed integer is undefined, because I guess you're shifting a 2's complement number left and right, and which can screw it up. So you actually have to do multiplication on this. The optimizations in the compiler, for all I know, turn that back into what I was trying to do in the first place. But between me, ChatGPT and bits of Stack Overflow and stuff, this seems to be the way that you're supposed to do it. One of the questions that I got asked quite a bit in my previous video is, why don't you do this using assembly? C is not doing it in hard mode. Assembly is doing it in hard mode. Yes, I know that is very, very true. However, it's crap like this that I'm quite glad I can write this in C. Because trying to debug whether I can do multiplication properly in assembly is going to take me ages to do. With this, I can just run this in Linux and see if it works and gives out the correct answers. So I'm using C because it lets me effectively write assembly just with words instead of lists and lists of mnemonics. It's all just like assigning variables, doing maths and moving things around memory. It is pretty much how you'd write assembly, just I'm writing it in a much more readable way. It's not like Windows programming where there's lots of calls to APIs and things. So this is the game as it is at the moment, or the game engine. We're making an engine to begin with. Let's rerun it, because there's a subtle thing that just happened. If I do make emulate, you can see it's writing text first, and then this appears. If I press escape, I have a debug screen. Ignore the massive flashing that's going on. There's a bit of a redraw problem, and I'm just ignoring it because this is a debug screen. This though lets me log text that I can read later on. And then I can get back to the game. Being able to do this took quite a lot of effort. I found several bugs in code that I didn't even know I'd put bugs into. But now I can start the game. So the magenta coloured thing is me. And you can see it moves around the screen with a little bit of sort of slidiness to it. And it actually feels quite nice to control. So it gently glides to a halt. If I ram into this green thing, nothing happens because it's not supposed to collide with that. But I can shoot it. And you can see the bullets disappear when they hit it. You can also weirdly see that it moves a bit. But we'll ignore that. If I also shoot, I move backwards slightly. So it's got a little bit of recoil to the thing that I'm firing. This one, I can push it around the screen. And if I whack it too hard, I get shunted around the side of it. You would not believe how satisfying it is being able to make this work. Because there was so many problems with getting this to happen. Things would stick to each other, stuff would just go bonkers, I'd flick through it and disappear off into the edge of the screen and never come back. Sometimes I'd touch it and everything would just crash. You'll notice there's a bit of overlap before I actually register being collided with anything. That's the size of the hitbox plus some of the overlap checking code. I'm just going to go with it. It's just going to be a feature of the game that things slightly touch each other like that. It might be that I just redraw the graphics so you can't tell. I'm going to hide a lot of the minor things that I don't want to fix at the moment. Because I've got the basic idea working. I've got things on the screen. I can drive them around the screen. And I can shoot stuff. And when I shoot, the stuff that's shooting goes away. So I can start to build this into a game. They can be bits of scenery, or they could be things to collect. I can represent text. If I shoot lots of things, the game doesn't lag because it's destroying those when they go off the edge. So it's quite cool. I know it's only 3 boxes on a screen, and it's all black and white, and you could make this in 2 seconds using Unity, but that's not the point. The point is that I'm learning all this stuff. I'm not just reusing a game engine and making a thing and that's it. I'm trying to learn how all this stuff works. That's my entire thing, innit? If you look back on my previous videos, I got a Z80 and I programmed it from scratch by literally typing binary into its editor. I like to know how all this deep level stuff works. But also, I want to make something with this now, which is why I'm using tools that help me to get on with this quicker. It's not like I'm just completely cheating, I'm only slightly cheating, just so that it happens faster than once a year. Because I've tried doing this stuff so many times and I've just got stuck. Now I have the tools to not get as stuck. Moving things using physics looks kind of cool. Things feel a bit more realistic. It makes more interesting gameplay. Resolving collisions using physics, a little bit trickier. This part took me a good few days to figure out. And by saying figure it out, it sounds like I'm weirdly flexing my own math skills, but I'll let you into a little secret. My math skills are not that great really. I had help from ChatGPT. But before you all roll your eyes and tell me I'm not doing this the hard way and that I'm faking it and everything else, I'll show you some transcripts of how I used ChatGPT, tell you a bit of a story. Because nothing that I'm doing here is new. I'm not inventing anything new. The maths is literally hundreds of years old. And the code has been used since computing prehistory. This is how you do this stuff. So if I want to know this knowledge, I've got a few options. I can go and Google it. I can read books that other people have written, which is really helpful. That helped me get the idea of how to do a physics thing. but it's only helpful to a point. If they've not written it down, I can't read it. And if I don't understand what I've read, I can't ask them what they've written. But this is where ChatGPT is actually quite useful, because sometimes I don't know what to ask. So I can give it some vague thought I've got in my brain, and it usually sort of suggests words that might be helpful. And I can use that to go and do some research. The physics code, I'm going to explain to you now by going through it like line by line on my computer. So I'll see you over there again. So let's get to the actual like meaty bit of code. This is all the physics stuff and how it kind of works together. I'm going to walk through the code. It's going to be really complex. I'm going to waffle for ages. I'll probably go off on random tangents, but this is like the good bit, okay? So in the game screen, there's this function I've got now which is called first run. It loads the sprites in, and then we get to the interesting bit. I'm instantiating one of the sprites. This one I'm calling player. And what that does, okay, so when we instantiate a sprite, what we do is we find one that isn't used, we set it to be active, we set its ID to be the sprite def ID that I've got, we get the data about that type of sprite, and then we reset everything to null, and then we return its ID. So at this point I've got like a handle to that instance. I can then construct what I'm calling a physics body, which has got some information. So if we go and find this thing, physics create body. So when I make a physics body, I'm storing this data about the physics item. So in most game engines, so I've stolen the idea as well, you have a sprite, which is the thing you see on the screen and the thing that you interact with. It separately has all the data to do with physics as a separate thing. So that's a physics body. And in there we store the position, we store what it's called its half size, which is like half its width and height. And then I've got some vectors, so I've got velocity and force, and then some numbers which are its damping, so that when it moves it slows down. Its mass, which we store as the inverse, which is where you do 1 over the mass. And then restitution, which is how bouncy it is. Some of these things sound far more exciting than they really are in my code at the moment. We'll come to the cheating bit later. So we create a physics body, and I'm saying 1010. So what is that? So that's where I want it on the screen. Then I'm going to set the damping and the mass. So I've randomly decided it's going to be at point position 1010 on the screen. It's got a damping of 0.9, so it gently slows down, and it weighs 10. I don't know what 10 it weighs, but it weighs 10 of them. That's a really confusing part about this. Like, there's no scale to this. There's no meters per second, there's no centimeters, whatever. It's just there's numbers, and I fiddle with them till the game feels like it should do. So I don't know what 10 means. It's not any units, it's just 10. I then have to link the physics body to the player. Right, so once we link the sprite and the physics together using this function, all we're doing is setting a pointer, and then we're calculating half the width and height of the sprite. So we're using the collision rectangle that I defined using a sprite, and then dividing it by 2, converting it to a fixed point number, and storing that. We're also setting the sprite's position from its physics position. I decided that maybe one day I want sprites that don't have physics in them, so there's a position variable for the sprite, which is just a copy of the one out of the physics body. I don't know, I may never use this, I may remove it in the future, but for now we're having a copy of it. It doesn't really do much. Once I've done that, the system sort of knows there's a physics object that needs something doing to it. And that's what happens inside the update function of the screen, where I call sprite system update. All we do is we go through all the sprites. If it's active and it's got a physics body, we then integrate the physics. And to integrate the physics, we do some really basic sort of Newtonian physics type of stuff. The position has its velocity added to it. We calculate the acceleration by multiplying the force by the mass. We then add the acceleration to the velocity, and we multiply the velocity by damping. What this just means is that the velocity is how much it's moving that frame, so we add that to its position, and then we calculate the velocity for the next frame. I don't know why you do this after setting the position, but apparently it doesn't really matter which way up you do it, but this is the way everything's done. In physics books and in other programming things, you'll see a delta time mentioned, which is the time between each frame. I don't have that in this system because I couldn't figure it out, and it seems to work fine without it. So that's how we integrate it. We do that for every single physics body in the game. We then need to draw this stuff on the screen. So in the draw function, we go through every sprite. If it's active and it's visible, we get the position from its physics body and we offset it by the middle of the sprite. So I'm trying to draw everything with the middle of the sprite being the origin, not the bottom left or top left corner. We have to convert it from a fixed point number, and then I tell the sprite drawing function to draw it. And all that does is simply uses the VDP to plot a bitmap at that position. So you can see the physics system is not that complex at the moment. It does just enough to make things move around the screen. One of the really hard parts about writing any of this code is that when stuff stops working, it just locks up and it's stopped, and I don't know why, and I can't printf anywhere because there's nowhere for it to go to. So I built my own system. I've got like a debug screen. If I run the game, there's the debug screen. I can see stuff happening. So I have a debug print or debug log that works like printf. So I can say when things are happening and what's gone on. So code that loads data off disk, if it finds a problem with a file, it can now tell me that there's something wrong. So if I change that file name and I now run it, it should tell me. There. You see, I can see on the screen that looks wrong. There's something not quite right going on here. If I look in here, you can see that I started the keyboard and I initialized the sprite, and I said I'm loading this file. I can't open that file and I failed to load it. Now actually I've just decided maybe that shouldn't like carry on working. It should actually just crash. Right, so what I've added is a tiny little bit of code. I now actually use my own error checking, which I wrote. You know, if you write your own code, you've actually got to follow the rules of it. So this returns an error code if it can't load the font. I now set this global variable called fatal error halt, and I switch to the debug screen. If I just go into the debug screen, I change it to the text mode so I can print nice text. I clear it, and then I've got this bit at the top. So if we're on an error halt screen, we write that on the top of the screen, otherwise we write that. And then if it is an error screen, we just sit in an endless loop and we literally just like crash the program so it stops. So now that I've like incorrectly typed in the file name for the font, this should now crash and stop. Which it doesn't. Isn't it great when you're debugging your debugger and that doesn't work? Let's just look in here. Main.c. So now if I check that that returns 1, I'm a bit confused now. I've been thinking for too long. You know, if you've got a function in C that's working properly, it returns 0, right? And if it's broken, it returns 1. That's how it should be, yes? So anyway, if it returns 1, we set fatal error halt, and we set the current screen to be the debug screen. Otherwise, we define the screens, we go on the title screen, everything's happy. I need to go in the main loop, because I have to call run screens, so that it can load things up. This is the code that switches between the debug screen and whatever screen I was previously on. So now when I run this, it goes straight to here, and it tells me it can't load that file. So I can now look at that and go, oh what the hell, what's .fn? That should be .fon. So I now have this system where I can tell if the game is actually like started properly or whether it's crashed. And I can print things to a screen that I can get to. I've got this bit here that says if you can still read this, it's crashed, because it might crash before it's like able to initialize the screen system that I've got. So you can see it's like on this bit very quickly. It initializes the screens and says they're okay. It might be that in there something goes wrong, like if I go into screen.c. So when we define a screen, we first check we can load we can create a new screen. If we can't, we might have run out of memory. So we go to a debug screen. Or we might have too many screens. So we go to a debug screen. It's more likely that I'm trying to set a screen that doesn't exist. Or when I'm in the run screens thing, there isn't a current screen because something's gone wrong. I've tried to switch to something that doesn't exist in a way that I'm not supposed to. So I can catch that. Or the update has returned the wrong number. So if we go into the menu screen, so here's a title screen. When you press Z, you're supposed to go to game screen because I've made some defines for it. If I change that to be a thing that doesn't exist, so there is no screen 5. Maybe I mistyped something and I don't realise. It now stops. And look, it says like, oh dear, Faltal, whoops. I'm going to keep that in, that's going to stay. It's going to be Faltal errors now. That's staying. So it says here, trying to switch to unused screen 5, cannot continue, halted. So I now know, otherwise it would have just crashed. And I wouldn't know why, so now I can see why. Debugging system, I've already used it quite a lot, trying to get the physics working, because I could print out when collisions were happening, or what the vectors should have been after a collision. So it's already been worth doing. I was spending quite a while deciding whether I should put the effort in to make it or not, because it took like a day to write that thing and make it actually work properly, not crash it by itself. But now I've got it, it saved me like more than a day's worth of effort. So sometimes you've got to weigh this kind of thing up, of whether it's worth making some more infrastructure or worth just persevering with what you've got. So in this case it was worth it. Part of what I like to show is all my mistakes, because it makes it more interesting. It also shows that I don't actually always know what I'm doing, but I can generally figure things out, and that's a useful skill to know. And when writing code like this, there's quite a lot of problems. Some of them are quite amusing as things like go out of control, or they stick to each other and they spin round and you just generally have code that breaks. Solving these issues is really hard. I'll explain in a future video some of my strategies for dealing with like code that doesn't work. But just know, if you're starting out programming and you find it hard, that's normal and it's okay, and it's just kind of programming, you know, it's a bit tricky. Doesn't mean you can't do it, it just might take you a while. And talking of things taking a while, I've been making videos since 2020, and my last video has done insanely well, better than any other video I've ever made. Clearly, you all like watching videos about making things using code, which is pretty good, since I like writing code, and I like explaining what I've done. So this seems to work very well, doesn't it? And to be honest, it was a bit crap over summer trying to get my computer replaced, because if it could have gone wrong, it did go wrong. And all the while I was quite aware I'd not made a new video, and I could look at my YouTube stats and see like all the graphs going downwards, which if you've not made YouTube videos, there's a whole separate like section of YouTube where you can see how well our videos are doing, and there's lots of graphs and charts and things. When it's going well, it looks wonderful. When it's not going well, it's possibly the most demoralising thing you can look at on the internet. When I put the last video out, I had no idea how well it would do, or whether YouTube would penalise me for not releasing a video for like 2.5 months. But if you're one of the, I think it's like 3,000 new subscribers I've gained since last time, then welcome. Hope you enjoy your stay. This is what I do. I write code and I talk about it and I wear nasty shirts. I also make the odd video about computer science related things. If you're not yet subscribed, keep watching, subscribe if you want. Don't rely on YouTube remembering to show my next video to you. Sometimes it'll get bored and decide you need to watch something else. If you left a comment on my last video, thank you very much. Knowing so many of you not only watched it but also wrote a comment is actually really motivating, especially those that are trying something similar or you used to do it as a job and you're looking at this going, who's this weirdo and he's writing about C claiming it's hard. Doesn't matter if you don't know C or you don't have an Agon Light, try making your own code and see it working after hours of frustrated debugging. It's really satisfying. Reading through your comments, you've given me some good ideas for the game itself. I'm going to have a go through those and I might pick some ideas out in my next video. But you've helped me work out a basic idea, so we'll see what that's like. But until next time, see you later. I write code and I talk about it and I wear nasty shirts. And I throw my project thing on the floor, but never mind. Oh, God's sake. Right. Let's redo that bit again.